that song, if I remember the story about that one correctly, the author of the story was supposed to go on a ocean voyage with his family. For whatever reason, he was unable to. So they left ahead with him. Without him, they went first, and he was going to join them. And whether I don't recall if it was in a storm or if it was a collision, but the ship sank and his entire family was lost. And he wrote this song after he found out that his entire family was lost. That still it is well with my soul, because he knew where they were. So I always an interesting story behind behind some of the hymns. So this week, first of all, I figured out how to get my things correctly up onto the screen there. I knew there was a setting. I just didn't want to mess with it last week. I did post on the Facebook page the link to the online book that I am going to be using as my big reference book for the hydroplates theory material that we're going to be using over the next few weeks. This is the 8th edition of it. This is the book. It is very heavy. This thing it's crazy information dense. There's a lot of things that I look at in this thing and my eyes start crossing. But his new edition is coming out. You can get the book. Somebody had asked about buying the book. It is available on Amazon. Apparently, because the edition is relatively old, it's used, and it's a textbook. Technically, it's a textbook. And if you know anything about college textbooks, used, this thing is $145 on Amazon. But if you go to creationscience.com, you get to that site. That's what it looks like. Okay? That's the new cover for the next edition, the 9th edition that's coming. And up there in that top right corner, there's a little person-looking thing. And if you click on that guy, and let me log out. As it's going to take its time today. All right, you click that little guy, and you get that. And you say sign up. You click sign up to view, and you make an account with an email and a password, and then you log in. And that's the book. That is the 9th edition of the textbook. I mean, that's the book. A print version is coming. I'm sure it's going to be about that same price. But that's it. There's the book. That's the 9th edition. And most of the time, having been one, most of the time college professors just make like 2 or 3 word changes in 8th edition to 9th edition, so that way the pages are in different spots, and they reorder the questions, so the questions are different numbers. So now you have to buy the new book, because when they give you the homework assignment of questions number 1, 4, 6, and 8, they're different in the 9th edition than the 8th, because professors have a vested interest in selling textbooks and making money, oftentimes, unfortunately. So we were, as I recall, not animations. That's where we were. We had stopped at we had talked a little bit about the questioning about the flood and is the flood real and that kind of stuff. So what we're going to be doing this week and next week is sort of reviewing plate tectonic theory. We're going back to 9th grade earth science. And we're going to take a look at the evidence that supports the plate tectonic theory. Now, what's interesting is what we're looking at, and I think we had talked about this last week, is that you sort of need to know what the other side is saying or believing in order to be able to refute their arguments. it makes it a lot easier if you know what they're going to argue to be able to argue back. And that's what we're going to be taking a look at. And we're going to look at how the hydroplate theory also explains the observations that we have, but from that catastrophism mindset, the biblical mindset, versus that secular long-term mindset. So the first thing we want to take a look at, because the flood wasn't just a flood. It didn't just deal with the surface of the earth and the flood. It also dealt with the atmosphere's circulation. It dealt with literally a huge overturn of how the earth worked. We had talked about how there was no rain prior to the flood. We had this mist that came up out of the ground, and that has changed. After the flood, the entire global circulation of the planet changed. So let's take a look at our atmosphere circulation. And the circulation of the earth, the upper air circulation of the earth, are referred to as Hadley cells. They're named after the meteorologist that first theorized this organization of the atmosphere. And it describes the large-scale circulation of our atmosphere. Where we live here, most of the time the wind comes from the west. Northwest, west, southwest, most of the time. The area we're in is an area called the prevailing westerlies. If you've ever gone down to the southern part of Florida, down into the Caribbean, anywhere down in there, the winds almost always come from the northeast. They're the northeast, what they call the trade winds. Between the two, like around Florida up to maybe just south of North Carolina, it's a relatively calm area. Out in the middle of the Atlantic, it's the Sargasso Sea. It's referred to as the doldrums. It's an area there's not an awful lot of wind most of the time. Now, there's individual weather systems, individual storms, but this is like big picture circulation. It's those observed wind belts, and they're driven with what are called convection cells. Ooh, we're getting into deep science here. Warm air rises, cold air sinks. That's convection. All right, hot air gets less dense, hot air rises, cold air sinks. That's why we put ceiling fans in the wintertime. We turn the ceiling fans so that they blow downwards. So they take the warm air at your ceiling and pull it down toward the floor. In the summertime, you turn ceiling fans the other way around. So it pulls the cool air from the floor upwards. All right, it sort of takes advantage of the fact that hot air rises and cold air sinks. This is the way our circulation, the way the Earth's circulation looks now, post-flood. So here's the Earth. And at the equator, hot air rises. At the poles, cold air sinks. The hot air rises, it goes toward the poles, it sinks, and it goes back toward the equator. Now that was the oversimplified version. They figured out that some of this air going toward the poles then sinks at around that 30 north area. That's that area we call the doldrums. Here's the northeast trades in the Caribbean. We're in the prevailing westerlies. And then up here are what are called the polar easterlies. And this boundary here between the polar easterlies and the prevailing westerlies, that's called the polar front. That's what gives us our wintertime weather. It's that battleground area that gives us our wintertime weather. That's the way the Earth is set up today. That's how it works today. If you look at a picture of the planet Jupiter, we can't really see those wind bands on the Earth because air, I mean, there's air in this room, but we can't see it. We see clouds, but we really can't see most of the Earth's atmosphere. But in Jupiter, because of the different things, the different gases that are in its atmosphere, we can actually see its atmosphere. And if you look at Jupiter, all of those individual bands, this is a big storm. It's called the Great Red Spot. That's called the Little Red Spot, because that one's big and that one's little. Sometimes scientists get really, really creative with their names. But each of these individual bands are just like that. It's just like our trade winds, our doldrums, our prevailing westerlies. Each one of those bands is exactly the same. And what's really cool is if you look at Jupiter, not in visible light, but in infrared. Infrared is heat. If you look at Jupiter in infrared, we really see it. The red areas are where the atmosphere is warmer, and the darker areas are where the atmosphere is cooler. And it's these areas where the atmosphere is rising and sinking and setting up these different circulation bands on Jupiter. Well, the Earth is exactly the same way. Again, this is post-flood. This is how our atmosphere works post-flood. Now, the other thing that we have to take a look at is the internal structure of the Earth. All right, and again, the reason why I'm going through this is because we sort of have to understand what the secular mindset is, what the non-biblical mindset is, the billions and billions, the long-term thing, to be able to compare and contrast that to hydroplate theory, because the big thing is we need to be able to come up with a theory, with a description of how the Earth works that not only matches up with what the Bible shows, but with what we see on the Earth. And if it doesn't do that, then the world is going to look at us and say, you're nuts. No, that's not right. That doesn't work that way. The Bible doesn't match up with the way the world is, so the Bible's got to be wrong. That's what they're going to say. And the neat thing is the hydroplate theory, solid geological physics-based theory that matches with the Bible and matches with what we see in the Earth's structure. So the Earth's structure, the way the Earth is set up, it's a layered ball. Right? If you were to cut the Earth in half, it's made up of different layers. From the surface moving inward, the outer layer is called the crust. It's very, very thin. It's a cool layer. It's the solid layer. It's what we see. It's everything we see here on the surface of the Earth. Underneath that is a layer called the mantle. The mantle is hot and it's soft. Now, I use the word plastic up there. And what I mean by plastic, I don't mean plastic like this. I don't mean plastic like the material we use. I mean plastic like the characteristic of the material. A plastic material is a solid material, but it's soft enough to deform. Think silly putty, all right? Think clay. Clay is a plastic material. It's solid. If I took a ball of clay and threw it at John and hit him in the head, it would hurt. But it's also going to deform. It's going to change shape. And that's the way the mantle is, all right? It's this soft plastic layer. The outer core is hot, it's liquid, and it's mostly nickel and iron. And then the inner core is also hot, but it's solid. It's also made of nickel and iron. It's the outer core and the inner core that produce our magnetic field. Now, interestingly, you look at a planet like Mars, if you took a compass and went on the surface of Mars with a compass to be able to figure out where you're going, it's not going to work. Same thing on the moon, because that outer and inner core is what produces our magnetic field. And if you look internal structure of the moon, it's not a thin crust, it's a very, very, very thick crust that's cold. And an inner core that's solid and pretty well, it's I would call it warm as opposed to hot. And by hot, I mean like 5,000-6,000 degrees. Center of the moon is more solid. There's no magnetic field on the moon. Same thing with Mars. Their explanation is the inner planets started out as these hot and molten balls and are gradually cooling off. And because Mars and the moon are smaller than the Earth, they've cooled off enough to the point where their central cores are solid. Whereas the Earth, because it's bigger, it's cooling slower. The mantle is that layer that's still cooling off, and yet you still have the hot, liquid inner and outer core. Again, that's their theory. So here's our layers. if they were drawn to scale, the crust between 5 and 25 miles thick, mantle about 1,800 miles thick, the outer core about 1,400 miles, the inner core about 800 miles. If this was drawn to scale, you wouldn't be able to see the crust. That layer is so incredibly, incredibly thin. Question is, how do we know? How do we know that's in there? The deepest we have ever drilled is only about a mile or two, maybe 3. The Russians tried to drill down to the boundary between the crust and the mantle. It's named after I think he was a Polish geologist. His name was Moho-Revicik. They call it the Moho. It's this boundary, the Moho-Revicik discontinuity. It's the boundary between the crust and the mantle. They tried to drill down to that. Didn't get there. Because the crust is anywhere from 5 to 25 miles thick. They drilled down about 3. So how do we know? How do we know? How do we know what's down inside there? Seismic waves, earthquakes. Earthquakes can tell us what's inside the earth. Did you ever get a present and you shake the box to try to figure out what's inside of it? Denise did that yesterday when I gave her Mother's Day gift. She's like, this is really light. And she shook it a little bit. Is there a Ferrari in it? I said, no. But we shake the box to try to figure out what's inside of it because it shakes around, it bumps around, and we can try to figure out what's inside of it. Well, that's exactly what we do. We look at earthquake waves. And there's 2 different kinds of earthquake waves. There's what are called S waves, and there's called P waves. S waves look like ocean waves, like this. They look like S's. That's why they call them S waves. Wow. P waves are compression waves. And the way I used to describe it for my physics students, S waves, the wave goes like this as it's moving forward through space. Okay? The material is vibrating up and down as the wave is moving forward. P waves are compression waves. P waves go like this. They vibrate this way. So the particles are vibrating back and forth like this as they're moving through space. Sound is a P wave. Okay? Sound is a P wave. They move at different speeds in different materials. So if we can analyze how those waves are moving, and what they do is they look at picking up, we know when an earthquake happens, and those earthquake waves take time to travel through the earth, and places at different distances away from the earthquake center get the waves at different times. And based on that, they can determine what material that wave traveled through. So that's how we know what the internal structure of the earth is made of. The other thing is that P waves can move through a liquid. Compression waves can move through a liquid. S waves can't. So, if we look at the inside of the earth, if an earthquake happens up here, what's called the epicenter, and those S waves come out and they go to different points on the earth's surface, but we know that if you go beyond, it's 103 degrees from the epicenter to here, if you go beyond that, no S wave. If you've got an earthquake station that's over here, it has no idea that that earthquake happened because the outer core is liquid. S waves can't travel through liquid. This shadow zone tells us that there's liquid somewhere inside the center of the earth. And we can determine, based on where that shadow zone is and what we know about the internal material, how big that area is. P waves can go through the core. And as they travel from one material to the other, they bend, all right? Waves bend as they travel from one material to another. It's called refraction. Waves bend. Light waves bend. It's the same process that makes it bends the light waves and breaks them up into the rainbow when we had looked at the creation of the rainbow being a new phenomenon. Same deal. we've got these bending waves, and the fact that, again, there's an area where there's no P waves tells us that there's two different layers in the inside, all right? These are guys that are a lot smarter than I am. They're able to figure this stuff out. And with computer analysis and stuff like that, literally this process that they're using to figure out what's in the inside of the earth is the exact same basic process they use with ultrasound. If you do an ultrasound to find out that you've got a kidney stone or a gallstone, or they do that with pregnant women looking at the baby, ultrasound is this. It's sound waves that go in, bounce off, and come back. And the computer is able to, by knowing about the material the body is made of and all that stuff, it's somehow able to make a picture of it. It's amazing to me. Same concept, except instead of using it as a diagnostic tool for the human body, we're using it as a diagnostic tool for inside the earth. And we can figure out what's inside the earth. Really cool stuff. And that's a great example. This whole stuff with earthquakes, they've been doing this for 100 years. And a lot of times people will say, oh, what does geology matter to me? I don't live in California, so we don't have earthquakes here. So I don't care about earthquakes. Why should I care about geology? Why should I care about earthquakes? Why should I care about why they're doing this? The same science that they use to be able to figure out this stuff is literally the same science that Ben Franklin used in making glasses, as my hearing aid falls off. And it's the same science that they use to produce ultrasound machines. So there's the scientific material, the scientific stuff that we learn, but then how to apply that science to different applications is where it gets really interesting and really important to us on an everyday basis. So now we know what the inside of the earth looks like. Now we've got this thing called plate tectonics. This is the one that we've got to take a little bit more in-depth look at today. We're going to continue next week and then go into the hydroplate material. This is what we've got to explain, because plate tectonics, it's a geological theory. It was first proposed in the early 20th century. And literally, it first came about, the mindset first came about as geologists looked at the earth, and particularly the Atlantic basin. And if you look at South America and Africa, they sort of look like they sort of could fit together. And scientists kind of looked at that and said, that's kind of interesting. That's strange. And that's where this first came about. The first thoughts about plate tectonics came out. And it became widely accepted by geologists in the 60s. And I can remember in my earth science class in the mid-70s when I was in ninth grade in high school, plate tectonics was relatively new. School textbooks sometimes don't get updated too quickly. And I remember our earth science textbooks were talking about plate tectonics as if it was a theory that had just come out, because it had. It was really just being widely accepted by geologists in the 60s. Thank you, U.S. Navy. They did undersea mapping, because as you started getting into the 50s and the 60s, the Navy is producing nuclear submarines that can dive deeper, that can stay underwater all the time, versus the diesel-powered submarines like the U-boats in World War II and the American submarines in World War II. They were diesel-powered. They were ships that could go underwater, as opposed to a really true submarine. They had to stay relatively close to the surface because they were run by batteries, or they would stick a snorkel up and run a diesel engine to run their engines on the submarine. So they really couldn't go all that deep, okay? World War II submarines, 3, 4, 5, 600 feet max. Modern U.S. Navy submarines, a lot deeper than that. Unclassified numbers, 8,000 feet. unclassified numbers. So they need to know what's down there because they don't want to run into stuff. It's happened. It happened. A U.S. Navy submarine going at 20, 25 knots literally ran into the side of an undersea mountain. They were able to get it to the surface, caused some significant damage to the submarine. But it happens. So the Navy, given they were going to be having submarines operating underwater longer, deeper, they needed to map the bottom of the ocean. The same way, by the way. Same as our ultrasound thing. You use sound waves, bounce them off the bottom, they bounce back up. The deeper the water is, the longer it takes the sound wave to hit the bottom and bounce back up. So they use the exact same process to map the bottom of the Earth's surface. And as they did that, they found several major features under the water. The ocean is not like a lake. Most lakes are shallow at the edge and they're deep in the middle. Okay, cool. It's not the way the Earth is. They found something called the mid-ocean ridge. It's a mountain range that literally encircles the planet. Think like the seam on a baseball. That's what it does. It literally goes all the way around the planet underwater, the mid-ocean ridge. The Atlantic Ocean is not at its shallowest, but it is shallower right in the middle of the ocean because there's a mountain ridge there. It also found things that are called trenches, areas that are very, 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 very deep. The Marianas Trench, the deepest place in the ocean, it's out near the Philippines. The Challenger Deep, which is that actual deepest spot, is about 37,000 feet deep. Mount Everest, 27,000 feet tall. Take Mount Everest and put it at the bottom of the Marianas Trench, it's still got 2 miles of water over top. Very, very, very deep areas. But they're near coastlines. They're not in the middle of the ocean. The Marianas Trench is right off the coast of the Philippines. The Japan Trench is right off the coast of Japan. The Chile Trench is on the Pacific Ocean side of South America. The Puerto Rico Trench is just north of the island of Puerto Rico. So we need to explain where did those features come from. And what's really cool is it's the thing that I've always sort of, to be honest, I've always liked about the plate tectonic theory is that those features had not been discovered, but they were predicted by plate tectonics. That's when you know you've got a pretty good theory. When you come up with something and say, well, if my theory is right, we're going to discover this other thing. We haven't found it yet, but we're going to discover this other thing. Some of our particle theory for these subatomic particles is like that, where they predict the existence of a particle and then they find it. And that really is validation that their theory, that their idea is right. And that's the thing with plate tectonics. Plate tectonics is not like the Big Bang Theory. The Big Bang Theory, I'm sorry, right on its face. Remember how the Big Bang got its name? Okay, that French physicist came up with astrophysicist came up with the idea that the universe started as this ultra-dense particle that suddenly explosively expanded. And when he presented that idea for the first time to the scientific community, their reaction was, are you stupid? Yeah, an explosive expansion. Yeah, right. You mean like a Big Bang? Remember, that's where the name came from. That's where the name of the theory came from. It was a term of derision. They were making fun of him. And the Big Bang Theory really, it's got a lot of problems to it. They keep trying to fix it and patch it up and all that stuff, but plate tectonics, it's a good one. It really, to be honest, it's got a lot of really good, strong evidence supporting it. Now, here's the Earth and everything underneath it. We see our continents, North America, South America, Africa. And here's this sort of a jigsaw puzzle fit. See how South America sort of looks like it would fit right here under Africa. And this part of Africa might fit like right in here, sort of, kind of. Here's our mid-ocean ridge. Starts from up here in the Arctic Ocean, comes down past Iceland, all the way down through the center of the Atlantic Ocean, down into the South Atlantic, and then it splits. Part of it goes up into the Indian Ocean, part of it goes this way, and then here it is in the Pacific Ocean. There's our mid-Atlantic ridge. And if you put that onto a globe, as opposed to a flat map like that, if you put that onto a globe, it literally looks like the seam of a baseball. If you pick a spot on a baseball and follow that seam all the way around, you eventually come back to your starting point. Well, it's the same thing. If you did that here, it eventually follows around. This ridge goes up here and goes up into the Arctic Ocean on the Pacific side, and eventually that connects around. It goes all the way around. It connects. This connects over here. And then here's our trenches. Here's the Chile Trench right here. Puerto Rico Trench is right there. This is the Aleutian Trench, the Japan Trench. Here's the Marianas Trench. The Challenger Deep is like right around in here. Okay, and there's a few out here in the Pacific. Okay, so we've got these trenches, and we've got funky things like the Red Sea, and how the Red Sea, and it almost looks like there's something going on from the Red Sea down here into Africa. All right. So the idea of plate tectonics is that the Earth is broken up into individual separate plates. The Earth's surface isn't solid, it's cracked. And that those individual plates move. Very similar to the Hadley cell theory, which is part of the reason why I mentioned it, it's the same idea of convection cells. There are areas of hot material rising in the mantle, and areas in the mantle that are cooler materials that sink, and it sets up this circular pattern that pushes, and as it moves, I'm going to put this down. As it comes up, it pushes on the plate, and then pushes outward like this, and the plates push outward. That's plate tectonic theory in a very small nutshell. The hot material is rising at the mid-ocean ridges. That's where the material is spreading apart. And the cooling material is sinking at the trenches. It's a very solid theory. And then other features are formed at plate boundaries when plates run into each other. Okay, mountains get formed at boundaries of plates. Now here's the Earth, and here's our plates. What's interesting is, again, over the years, they've found that, or theorized, that the Earth is not just broken up into these big plates, but there are small little, what they call microplates, because you have to, plate tectonic theory has to explain, because it explains earthquakes, it explains volcanoes, it explains all these different features. Great, but you got to explain little things like the biggest earthquake ever to occur in North America happened in what state? Missouri. What? Missouri? Looks like the middle of a plate to me. California is on a boundary. California is right at the boundary between the Pacific plate and the North American plate. And as those two things keep banging into each other and sliding past each other, the plates are sliding past each other and they stick, and all of a sudden they move. And that's an earthquake. Again, plate tectonics, great. It really explains this stuff insanely well. Well, the North American plate is cracked. It's not one big piece. It's cracked. And there's a real big crack right about here. It's called the New Madrid Fault. The strongest earthquake ever to occur in North America happened on the New Madrid Fault in the early 1800s. If it happened today, forget Los Angeles, San Francisco. We think about the San Francisco earthquake and the Northridge earthquake in LA, something like that. That thing cuts loose today. Nashville, St. Louis, St. Louis, Missouri, St. Louis, Kansas City, Kansas, Kansas City, Missouri, all that, gone, wiped. So they look at these little subplates, but this is the big picture, okay? The African plate, the South American plate. And where these plates bump into each other, we get features. The collision between the Nazca plate and the South American plate produces the Chile Trench. The collision between the Caribbean plate and the North American plate produces the Puerto Rico Trench. The collision between the Pacific plate and the North American plate produces the San Andreas Fault in California. The Indian plate colliding with the Eurasian plate creates the Himalayan mountains. So this is really pretty good. Now, this is a map, dots of earthquakes. And what's cool is where most of the earthquakes happening? At the plate boundaries. Most, not all, most. All right? Earthquakes and volcanoes happen at the plate boundaries. And we've got, here's our mid-ocean ridge, that baseball seam goes all the way around the planet, all right? And our trenches, our boundaries of the plates. That's why they had to try to explain, if I go back a screen, there's a little plate up here called the Juan de Fuca plate, because that little, not little, that big area of water that sticks into Washington State up by Seattle and Vancouver is called the Strait of Juan de Fuca. I guess that was the guy that discovered it, the Spanish explorer that discovered it. So they call it the Juan de Fuca plate because they had to explain why there were earthquakes inland near Washington, but then also a line of them sticking out into the ocean over here. They had to explain that. They said, oh, well, there's a little plate there, the Juan de Fuca plate. And when you put these two pictures next to each other, here's our plates, here's our earthquakes, and you see where, I mean, pretty darn good. It's a really good match. It really is. It's a really good match. The problem is, though, there are some things that you can't explain, and I'm going to go back a few screens here. I want to go back to go back here. The problem is, with some of our things here, the plate tectonics doesn't explain properly some of the other things that are going on. All right, and I'm going to tease a little bit some of the issues. We're going to continue with this next week because I'm going to laugh. Last week, I had a certain stop point I had to get to, so I ran long last week. Pastor came up to me afterwards. He says, I know you got a lot of stuff to cover, but can you guys maybe start on time so you can like actually end on time? And I kind of looked at him like, you're the one that's telling me to end on time? I had to laugh. I really did. I had to laugh. I didn't say anything, but I had to laugh. Here's one of the big problems with our plate tectonic theory, okay? What the heck is this thing? Here's this like straight line thing going from the Bay of Bengal down into the Indian Ocean. What is that? What about all of these guys? All these, they're called seamounts. Seamounts are underwater mountains. Usually they're underwater volcanoes, all right? What about stuff like the Azores? It's a volcanic mountain chain that's over here. It's not on the ridge, it's off of the ridge. And there's also little ones. There's an island down here in the middle of the Indian Ocean It's just there. Down here in the middle of the ocean. You got Ascension Island that's down here in the South Atlantic. You've got Tristan da Cunha down here, which is another little island chain that's in the middle of the ocean. If the rising material is at the mid-ocean ridges, why do we have things like Hawaii? The Hawaiian island chain here, set of volcanoes, and when you look underwater, the Hawaiian island chain goes all the way across here, and then it goes up toward the Aleutians. Most of that, like the Hawaii ends about here, and you got a couple little dot islands there, but then it bends and goes up that way. Why are those there? Those are in the middle of a plate. When we look at our plate tectonics, just like the New Madrid Fault, here's Hawaii right there. All right, and that it goes up this way, that line of and all here in the middle of the Pacific Plate, there's all these little volcanic islands. A lot of them are underwater. They're called seamounts. Those are the things the Navy wanted to know were there. All right. Plate tectonics doesn't explain everything. It does a great job. Go back one. It does a great job here, but it's got some holes. We're going to continue next week and talk a little bit more about how this looks. We're sort of looking at what we've looked at so far is sort of like my pictures of Jupiter and trying to talk about the cloud structures by looking at the tops. Well, what we've got to take a look at, I'm just going to tease. Whoops. Is that. That is for the earth what that was for the atmosphere. Looking at the structure, looking at how this is working. We're going to look at that next week and then sort of tease into how hydroplate theory deals with this and addresses it and shows the reality, what's actually going on. That's going to take us a few weeks as well, okay? I know it's a lot. It's a lot. How many heads are exploding? All right? It's a lot of stuff, okay? It's a lot of stuff. But as we get into hydroplate theory, by the way, make sure you study, because at the end of next week's session, we're having a quiz. Yeah, it's a pass-fail. But we're going to look at, as we're going through and as we talk about the things in the hydroplate theory, I'm going to be referring back to some plate tectonic stuff. And that's why I wanted to do this quick sort of refresher / overview of the plate tectonics theory, so that when we get into the hydroplate theory, a lot of it will make more sense as to why it describes it properly. Okay? I'm waiting for the face looking in the window going, yeah, exactly, he's going to. All right? Thank you so much, everybody. I appreciate. Again, we'll continue with this next week. Lord, we thank you so much for this day, for bringing us together today, for open minds, for open hearts, Lord, for helping us to be able to take this material, to be able to apply it, and not so much to apply it to our lives, Lord, but to be able to help us to see the truth to your word, Lord, that your Bible, not a science textbook, but it is still scientifically accurate, and that we can see how the earth works by your hand, and that the events that are described in the Bible, the flood specifically, are true, Lord. We know that they are, but this is sort of getting it into our sort of thick human skulls, a proof that we can look at. We don't need that proof, Lord. We have faith that we know that your Bible is true. But having that proof does help us to reinforce our faith, not to produce our faith. Pray that you'll be with our service today, be with Pastor, be with Larry as he's not feeling well. Please be with Ron and Esther with his medical situation, Lord, and all the other situations that we have in our church right now. All these things we ask in your son's name. Amen. Now hit the red button again. Actually, hit the black square.